Hi everyone. As Tad said, I'm Callum Watson. I work at the British Geological Survey, and this is some work I've done together with my colleagues, producing what we call a degree 2000 model of Earth's magnetic field. So that resolve features down to a wavelength of about 20 kilometers. That's the smallest it can go. So a bit about me. I have the very vague job title of geomagnetic scientist. And I work at BGS in Edinburgh, in Scotland, and I've been there for about 3 years. I largely produce global magnetic field models, so that's why I'm talking about that. And I do some research relating to that as well. I work with a wide range of partners. Work with you guys, with governments, with university researchers, with the European Space Agency. We've had chats with artists who want to know more about magnetic fields for their projects. Before that, I did a PhD in Cambridge in applied maths, together with some theoretical geophysics. And I was looking at the past history of particularly the Moon, but also to some degree Mars and Mercury. Sadly, I could not get PhD funding to go and do any field work out in the Moon for that, but I did some theory of mantle convection and how that coupled with the magnetic field generation through the core mantle boundary. But back to the present and to Earth. What is lithospheric magnetism? I mean, it's the Earth's magnetic field is quite a complicated thing, as many speakers have told us about. Several thousand kilometers below our feet is the outer core with lots of complicated turbulent convection of liquid iron. Above our heads, there's all sorts of complicated plasma physics to do with the interaction between the atmosphere and the sun and the solar wind. But the lithospheric magnetism, which includes a lot of Earth's crust too, is much simpler. It's just magnetized rocks that are nice smaller distances below our feet, and it contributes on average about 0.2% of the total magnetic field strength you see at the surface, so around about 100 nanoteslas, but it's very regionally variable. There are places where it can be 20% of that field strength and makes a major difference to the magnetic field globally. And because we are sitting right on top of it, rather than it being thousands of kilometers below our feet, we can see a lot more detail. Very roughly, the sort of distance scales that you can see in the magnetic fields are about the same as the distance between the source and the observer. So, for example, with the magnetic field of Earth's core, that's about 3,000 kilometers down. We struggle to see features that are much smaller than 3,000 kilometers. But with Earth's crust, you can see magnetic fields of grains in rock if you're looking for things that small. The one big saving grace, though, that makes it much simpler to deal with in a way is that the lithospheric magnetic field only changes on geological timescales. So you'd have to open up a new rift valley or have a new volcano built up for have some metamorphosis of rocks happening to make any significant changes to it. And that's unlike when waves can propagate much more rapidly in the outer core, or solar storms can change things in the space of a matter of days. And well, why do we find it interesting here? I mean, I guess by far the main point that will matter at this conference is that it affects the direction of magnetic north. And again, this varies a lot locally, but in some places it can cause a difference of several degrees, especially at higher latitudes where the horizontal component of the magnetic field is weaker. Because it is generated by magnetic rocks as well, we can also find interesting things in geology just from the magnetic field. For example, certain major iron ore bodies have a huge signature in the magnetic field. You can see rift valleys, and you can see the history of the oceanic crust as well. And the last point in here is that it is also actually useful for understanding the other parts of the magnetic field, because especially the larger scale components of the lithospheric magnetic field are they can cause correlated noise in our measurements with, for example, with satellite data. And we need to take that into account when trying to calculate what Earth's core is up to. So I have a bit of a background here as to how we build up these magnetic field models. There are a set of mathematical functions called spherical harmonic basis functions, which I have some small pictures of at the bottom right here. Each of these functions has a parameter known as its degree. There was a picture of degree 0 there, but degree 0 doesn't apply to magnetism. So they start from 1, and I'm talking about numbers up to about 2000. And this degree is roughly how many wavelengths you can fit into the circumference of the Earth. That's why, with a 40,000 kilometers distance around the Earth, that's why degree 2000 comes out as a wavelength about 20 kilometers. But the larger degree you go to, the more different parameters you need. I have a picture here up to about degree 42, which even at this distance from the screen, I'm struggling to see the stripes on that. You'd have to zoom way in on a picture of the Earth to see degree 2000. The number of coefficients is about this, roughly speaking, is n squared for a big number n. So for a degree 2000 model, we would want about 4 million coefficients. And that, just by comparison, a picture of Earth's core's magnetic field, at the top right from the International Geomagnetic Reference Field. It's a model that goes to degree 13. That world picture there has, at any given moment in time, that has only 195 coefficients. So it's many thousand times more computation to get the crustal field than that. And no model would be good with a good initial data set. We are starting from something called the World Digital Magnetic Anomaly Map, which even has its own website. This is a major effort by some other scientists, not myself, but the difficulty here is that, again, because of this problem where you can only see features that are down to about a length scale of the distance away from it that you are, satellites cannot see the fine detail in the lithospheric magnetic field. So it needs to be survey data from all around the world, and these come from all sorts of different time periods, all sorts of different methods, whether that's aircraft or ground surveys or marine surveys. They need to be carefully stitched together. People have to negotiate with a variety of governments and companies to see what data they were willing to share publicly. And they had to very carefully get it to stitch together properly without leaving step discontinuities at, for example, national borders. And the resulting thing has, the resulting data set has about 26 million data points on a grid that has a resolution of around about 5 kilometers. It's at a fixed altitude over land and sea level at sea. And they released an update to this model in March last year. To get from, well, something that we're going to do to make this a bit more useful is to take this scalar-only data at a fixed altitude, at a fixed grid, and turn it into a fully three-dimensional model, so you can get a magnetic field value of your declination and dip and field strength at any given point on or above or below the surface. And this requires a large amount of computation. BGS have done some work with this in the past, but we were limited by just the sheer computation time and expense. So we did a collaboration with some researchers at the University of Edinburgh on improving the computational performance of this. And there's a paper just about the code. And we've since done some further work which has improved that again. We now have a new, faster, high-performance computing cluster, which makes it faster yet again. So we can now actually go about 100 times faster than before at calculating these models. And that, of course, means that we can now produce more detailed models than we did before. And going to degree 2000, there are other difficulties, such as the order that you add up the numbers in begins to matter with these spherical harmonic basis functions at such a high degree, because the ranges between very big numbers and very small numbers start to reach the limitations you can get to with floating point numbers in a computer. But we worked through those problems, and we now have some model results that I'd share. At the top right here, I have a picture from the World Digital Magnetic Anomaly map. That's the input data I use for this model. That's just scalar data on a grid. I've actually ignored the altitude there, so that's sea level and sea and 5 kilometers altitude and land. At the bottom right is the model output evaluated at sea level, so technically a slightly different thing. And again, it's the scalar anomaly relative to the core magnetic field there. And as you can see, it does look like more or less the same picture. You look very, very closely to see a difference, but we thought that looked very promising to start with. And we thought we might try comparing this against some of our previous modelling efforts. We've done models to degree 1440 before with an older data set. So we tried looking at just an example here. This is Alberta, and this is in a place where there is not additional data versus what we were using before. And what you can expect here is a very slight sharpening of the previous picture we had, and I think that's more or less exactly how that looks. It's a very similar picture, but nothing too exciting there, and that's what I would hope. But there are places where the newer data set has fixed some issues that were used previously. Maybe I'll see here on this is a map of northern Alaska on the left, and the right thing, which picture is the northwest territories of Canada. Around this area here, there's a localized anomaly to the anomaly, an area where some of the data was perhaps not so well stitched together in the past, which has now been improved with the new improved data set that we have. So we thought we'd try and have a look at how this affects our model. So we have the model's declination anomaly relative to the core magnetic field here, and in this same area offshore, you can see that a large blue feature, which was a westward part of declination, is no longer there, but in the rest of the map, the same features are being picked up. And perhaps a sort of in-between example is just a picture of Western Europe here. The data is similar in large parts of this picture to how it was before, but particularly, I think it's the Atlantic north and west of Shetland, right? Roughly, I'll point this out in the map. So this is Shetland here, and roughly speaking, to the north and to the west of that, out in the Atlantic, the data set is a bit different there, and you can see this has caused the model to now have a different picture of what the crustal declination anomaly looks like. There are, of course, some further steps that we can take to try and improve this model further. Wouldn't be somewhat academic if I didn't have more ideas of what we could do. But the World Digital Magnetic Anomaly map that we started from has a wide variety of data sources, which are different ages, different instrumentations. In some parts of the world, there actually just isn't any survey data. I should add, it's filled in with satellite data. And this means that we should probably consider doing different sorts of weighting on that data. There's also the model regularization, which is a very important thing for crustal field modeling. It's a means of smoothing the data, but also trying to ensure that what you have is as physically accurate as possible. And there are there are many different ways of doing that, and we need to make sure we're doing that the best way we can. Thanks to the work we've done on making this much more computationally feasible, we can now just the regularization and incorporating data much more quickly and easily than just get onto my conclusion slides. I seem to have gone a bit too quickly perhaps here, but we've taken a scalar data set and computed this lovely 3D world model. And it's down to a wavelength of about 20 kilometers. And we are now capable of updating this much more easily than we could before. Thank you. So, any questions?
Round number.
Yeah, it's a nice number. I suppose the ultimate upper bound just now is to do with this issue with the floating point numbers. So if there's a problem known as non-associativity, if you have A plus B plus C, A plus B plus C does not equal A plus B plus C with these numbers. And sorry, that might not have been very clear there, but it's round about degree, I think 2,700 or 2,800, even the adjustments we're making would no longer be so valid, and that would become a major issue. I guess as well, there's the speed of evaluating a magnetic field model begins to become a major issue with large degrees. I think we can get a value out in about 30 milliseconds at degree 2000, but that's, I mean, very roughly that would double that to about 2,700, 2,800. Yeah, it is a bit arbitrary, but there are definite harder upper bounds if we go further.
So you think that this grid DDN it contains high degree information, and you are not able to extract, not able, I don't know, you are not extracting it because of numeric starting or some other considerations, but the information is there. That the correct state.
The information is theoretically there, but at a very, very high degree, we're relying a lot on every single data point being absolutely as accurate as possible. This is also as a compromise in not overfitting to the data.
Yes.
Hi, we're with DGI. It's more of a comment than a question, but now that we're having more and more of these models with various resolutions, I'm just thinking about how we're going to tie that into our VR models in the future. Because SRG and LRG and HRG and now we're slotted somewhere in between HRG and IFR1 or something else. But yeah, just thinking about that there. And then is this going to be released with the next model?
I can't say anything with certainty there, but we're hoping to include either 100% to 0 or perhaps an improved version at some point in future. I know that in the past we've done some error validations by checking the sort of model against various survey and repeat data that was not included in calculating the model, but we've not got as far as producing an error model based on this yet.
So yeah, you mentioned regularization in talk and increased critical and that you need to make some assumptions about the spectrum distinction spectrum of your density. And so include this to put assumptions.
That's a very good question. I haven't done a plot of the spectrum on this talk. One of the very hard things with spectra at this sort of degree as well is that the fact that the Earth is very slightly flat. It's an ellipsoid, and this means that something we found is that the spectra, you can have two models, one with a higher power spectrum than another, in which, when evaluated on the WGS84 ellipsoid, the higher spectrum is not necessarily a more powerful magnetic field on average. We need to come up with a sort of ellipsoidal version of our theories about power spectra before we can go too far with that. I know that, for example, there have been a variety of studies into what the theoretical power spectrum should look like, but they're a bit, we still have some unknowns about that at this stage.
So it would be, because you're going to change some BGM plugins, right? So if you're applying BGM plugin on the 6 normal to calculate the I-1 values, for example, since this is going to be such a major change, what would be the practicality? Have you guys looked at the practicalities as to how much will be impacted from what you, how much will impact the actual level of overall? The definition from the biggest errors and as that's one of the spacing.
I mean, yes, because the crustal magnetic field is not time variable, this does mean that past wellbores would now have different values. If that, let's see, so we'll start that. Ideally, we only want to put out an updated crustal field model if it makes a practical improvement to our understanding of the declination. For example, that map of northern Alaska that I showed does imply the need that we should try and update our maps of at least that region. And there are other parts that are all with new and improved data too. We haven't done a test with this with IFR yet, but we would only roll this out commercially if we had a good chat with all the affected companies beforehand.
Because as we haven't talked about that years, right? That the general, however, so maybe there's a little bit of change in the way you calculate it because it's a better model because it's much more refined. But I think for us, because of application, we will still need to look at it because it's right our calculation concept. And then that becomes so rapid, right? So in April 2027, you implement the 27 model, but then we just got surveys. Let's say we order the I-1 crustal values in February, March 2027. And the recommendation is to reprocess them, reclass them, and how much will it actually change? Or well,
yeah, Jerry Corlin, Albert and Anomaly. And that's probably several companies here will incorporate the GS code and in the coefficient file. If you raise it from 1440 to 2000, do we need the code or can we use the old code to process this to get back into swap predictions?
If or when we do roll anything involving this degree 2000 model out commercially, it would require at least a slight update to modeling codes in order to make sure that we are taking into account the floating point difficulties that I mentioned there. I know that we do have some written working code that does work with this, but that's not been shipped out yet because we've not shipped this out.
I'm just going to jump in there, just to say that if there any improvement or upgrades to the code, it would happen in the consultation with industry. So it wouldn't be just yeah, absolutely. So there's a consultation period before. So we have the updates and to the 2020, and that we want to do one lesson. Really, as also use this same very set we are making the model now capturing all of the spectrum. And so the harmonic properties handle it's still the change it changes the base portion of the bit that changes the harmonic properties handle largely obviously independent, so it would change between now to the question of how much it would change between now change and calculation is changing the part of that. Now we can do a little bit actually more of the possibly a waiver.
Thank you, Archie. That was very useful.
Very nice. So kind of a summary of what I heard from Kyle and Jared. I started because so the addition of large numbers wasn't in the processing to get you to the 3D model. It's actually in the if you give us a coefficient model, it's in the normal synthesis. If we want point calculations, that's the update to code. So as I was mentioning, we've done it before, so it's not huge. The question I think, I guess, is the files are getting enormous. I guess there's no reason why if we said 2000 was just not necessary. You could back it off with the new data back to 1440. We could leave the code and we would get the improvements from the anomaly model. Is that right?
Yes, that's absolutely right. We could truncate it, or something that has kind of is a side effect of or improvements to calculating the model from the data as well is that we do also now have again, this has not been shipped out anywhere, but we do have some code that is being tested that also runs faster with the same sort of models. I'm not sure how much I can speculate on what sort of commercial choices we might make, but certainly from the mathematical perspective, truncating things should be very straightforward.
So you have the grid, the data now. Is that something that's available now? At whatever state it's in, you know, it wouldn't be a synthesis model. It would be your 2.5 million points, but your grid ready. There's a lookup table essentially. Is that available?
And we've not published this, but certainly, I think we've done similar work with IFR doing that type of thing. So we could do a pre-computed grid for a region, perhaps. Or...
Well, I'm just thinking about trying to make the decisions for the future. You know, look at the areas that we're doing. How much is the change? And the other question about that is that I assume that we would then continue to get updated certain values also.
Sorry, I'm not sure if I followed the entire thing you're asking there.
Publishing out uncertainty of the model. So the online tool is here's the projected values, secular change rates, and uncertainty values. And those are what we can plug into our arrow. So we just get this that's taken into account the structural analysis. Maybe the uncertainty would go down.
I would certainly hope that uncertainty would be lower, otherwise this would be a waste of time. But yes, we can perhaps we can have a chat during the coffee break.
Thank you.